Yeah, in this session, let's primarily focus on analysis of variance. What is the prime purpose of getting into analysis of variance? See, in regression and correlation, we tried finding out the relationship between two variables, right? Or probably when we did hypothesis testing, we did the comparison between two variables or two population data. But if there is a requirement that I have to test the means of more than two populations, if I have to test or compare the various samples and compare the means across the various samples where the size of the sample is different, and my comparison is each of the sample means, I'll compare it with the overall mean of the total set of samples. That is where I use the one-way analysis of variance. So the terms wise, people use the term as treatments. Treatments are nothing but different groups of samples, and for each of the treatment, let's say I have multiple observations. If you see in the example here, I'm talking about the three different cricketers. So the sample, the treatments are three different cricketers are three different treatments, and the runs scored by each of these cricketers is the various responses or observations of each of the treatments. The sizes of each of the treatments are different. Let's say if we see Dhawan, there are 8, 9, 10, 11, 12, 13 instances. Whereas when it comes to Rohit, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 are there. So which means the number of instances or the number of samples or number of responses for each of the treatment are typically maybe different also. But my intention here is to compare whether the mean of each of these treatments is overall in line with the overall mean of the three put together. In those kind of scenarios, we resort to a one-way ANOVA or one-way analysis of variance kind of a procedure. So going ahead, probably I will try to solve this one numerical using the entire concept of ANOVA. So that is where let me jot down the numbers so that we can do our entire calculation on this data itself. So let me take the data regarding the three cricketers. So we would like to work out on the complete ANOVA on these three. All right. So I'll take, let me just copy the data. Let's say I have this kind of a data for these three players. Now, in this, some of the key terminology we need to be comfortable with as a part of the ANOVA analysis for us is K. One is the K. This is the word typically used. This is the letter that is typically used to denote the number of treatments. So we have three different treatments. N. N is the total sample size, all across all the things put together. The total sample size is 41. So the sum of all. So probably we have some number for Dhawan, some number for Rohit. Like that, we have around 41 total observations that were collected. And when I say Ni, N1, N2, N3, which is the sample size of each of them. So there is 14 for N1, there is 13 in N2, and there is again 14 in N3. So this is one more thing. And the way we represent each of the individual observations, right? We represent each of the observations by Yij. So I represents the treatment here. So there are 3 treatments. So probably when I say Y32, it means the third treatment, second observation, which is nothing but 52. So please be comfortable with that kind of a terminology. So when I say Y27, which means the second treatment, seventh observation, which is 2. So like that we should be comfortable when we are doing this ANOVA analysis. Our intention is to compare whether the mean run scored of Dhawan is same as that of Kohli and Rohit. That is the major intention in this analysis. Is the average of each of these 3 players more or less the same, and is it equal more or less to the overall mean of the population? So those are some of the things we are interested in. So from that standpoint, couple of calculations that are required for us are probably the mean of the first one. The mean of the first set, if I take the average of this data, it is around 50.5. When I take the mean of the second set, which is mean of Kohli, the mean of Kohli comes out to 40.07, and the third mean, which is mean of Rohit, the mean number of runs scored by Rohit comes out to around 35.21. And I want to check out the overall mean also here, not just the 3 individual ones. I would like to compare the overall mean also, which is nothing but the average of all these values involved. So we have to add up all of them and compute the average of each one of them separately. So that comes out to around 41.97. So this is one aspect of our calculation. We find out the average. We find out the average in this kind of a model. We find out individual averages, individual means, as well as the overall mean of the entire data. Apart from that, we also compute what is called as the treatment effect. We call what is called as a treatment effect. So we can say the treatment effect of the one. The first one, whenever we use the word treatment effect, it is nothing but the individual mean minus the overall mean. The individual treatment mean minus the overall data mean. So the TE1 in our case comes out to positive 8.5. TE2 comes out to overall mean minus the individual mean minus the overall mean minus 1.89, and the T3 works out to 35.21 minus 41.97, working out to minus 6.76. Now one small thing you have to observe is these are the 3 treatment effects for the 3 players whom we have highlighted, and as per basic arithmetic, the sum of all the treatment effects should be equal to 0 itself. If I add up all these 3, the sum of all the treatment effects more or less will come closer to 0 also. So this is a very small difference. And if there was no difference between the treatment means, then all of them would be same as the overall mean, which means the treatment effects across also should be equal to 0 itself. But in this case, there are some positives, there are some negatives, as well as for each of the treatment effects. And in some cases, they are very high also. The treatment effect of 1 is around 8.52, whereas of 3 it is around minus 6.76. Now, now we'll go back to, if at all I have to use the ANOVA analysis, a few assumptions are there, right? In my data also, I'm assuming that the data, whatever I'm working out, it is following all these three assumptions. It is following all these three assumptions. The populations must be coming from a normal distribution, right? So I'm assuming that the data that I picked up for Dhawan, Kohli and Rohit internally is coming from a normal distribution itself. The variance for each of these three sets of people is more or less the same. Only in these cases, the ANOVA is applicable for us. If the variance across the three sets of data is more or less the same, and if the populations are following a normal distribution, and the observations are independent, here at least we can make out that the runs scored in one match is completely independent of the runs scored in the other match. So at least the independence between the runs scored is clearly observed. But what needs to be understood is even the population should come from a normal distribution, and they should have a common variance. And once these assumptions are taken care of, apart from this, we should be comfortable even with a slightly different kind of terminology also here. We typically use the words like yi dot. Whenever we use the word yi dot or y dot j, we said each item is represented by yij. I is the treatment and j is the instance of that particular treatment. So, whenever someone puts a dot instead of the second variable, it means that it's the sum of all the values of that particular observation. So, whenever someone is saying yi dot, it means the summation of yij itself. So, in our example, whenever we say I'll write down some of the observations. If I put y1 dot, then it means the summation of all the first observations, all the first treatment, the total run scored corresponding to the first treatment. When I say y2 dot, it's again the summation of all the observations corresponding to the second treatment. And similarly, y3 dot also refers to the summation of the third treatment. All observations corresponding to the second and the third treatment. Similarly, if someone says y dot 1 means the first instance of all the treatments, the summation of the first instance of all the treatments. In some cases, it may not even have much of a meaning associated. So y dot 1 is nothing but the first instance of all the treatments put together, which is working out to 210. Similarly, sometimes people talk about y dot dot kind of a notation. When both of them are dots, it's the total sum of all observations across all the treatments. So this is working out to around 1721. Now the same logic, if these things are put up with a bar, on their top, it is nothing but instead of summation, you have to do the average. So if it is like y1 dot with a bar on the top, because I cannot put it here, I'm just writing out as bar, but with a bar on the top, then it is nothing but the summation divided by total. So here the total observations are 14. So I'm dividing it by the total observations 14, working out to 50.5, which is nothing but the mean. Similarly, when someone says y2 dot bar, which is nothing but this divided by the total observations 13, like that. Now when someone is saying here y dot dot bar, which is also nothing but the total summation divided by the total number of observations, which is 41, which is giving me the overall average of the total also. So the notations is something which we have to be comfortable with, and once we are clear on each of these notations, so all these calculations we should be comfortable with y1 yi dot, where it is the summation of yij for all j. Like that, when we are doing all these things, it becomes slightly easier for us in each of these activities. And now what we are trying to do is, we are also looking at, once we have computed the total mean across all observations and we have identified the treatment effect, we are also trying to find out the total variability that is there across each of the observations. Now, how do I identify the total variability across each of the observations? That is what we are coming out with. Now, let's say this is the overall mean, right? This is the overall mean. Now, what we are saying is, I'll insert few new. I'll insert few new columns here. Now we know that this is the overall mean 41.97. What we are trying to do is, we are trying to find out the overall variance first. The overall variance is what we are calling as the total sum of squares. Let me try it. So each observation, I subtract the overall mean. This is my overall mean. I subtract the overall mean and I do a squaring. So this is one thing which we are doing across. Alright, for all the observations, we are subtracting the overall mean from each of the observations and doing the squaring. The same logic I can do for each of these observations. So this is for each. Let's say curly is 31 minus the overall value is 41.97. So the 31 is the instant. 31 minus 41.97, around 11. The square of that 11 comes out to be this. So in this particular summation, where each value I subtract the overall mean of the population, from each value I subtract the overall mean and do a squaring. I typically call it as total sum of squares. What is the total sum of squares in this aspect? Or sometimes we write it as SST. SST is nothing but the total sum of squares. I'll add up all these values, and this is what I call as total sum of squares. In this case, it is coming out to 42,844. That is the way we arrive at computing the total sum of squares, which is nothing but from the each of the observations, I subtract the overall mean of the data and do a squaring, and after that I do a addition up. So the total sum of squares is coming out to that number. Then the next important aspect that we have to bring out is the sum of squares between the observations. The sum of squares between the observations is what we are trying to come out with. How do I arrive at sum of squares between the observations? I multiply the size of each of the treatments, right? I multiply the size 14 here, 13 here, 14 here, the size of each of the treatments with whatever is the sum of squares corresponding to the overall mean and that particular treatment mean. So how am I looking at? The first one is coming out to 14 times, which is nothing but the first the n1. n1 times, what is that I am finding out? The mean y1 bar. y1 bar, which is nothing but the mean of the first one minus the overall mean whole squared. Now the same way, the n2, which is this one, multiplied by the mean of the second minus the overall mean whole squared plus n3 times the mean of the third minus the overall mean whole squared. This is what is giving rise to the SSB, which is the sum of squares between the treatments. The sum of squares between the treatments is coming out to 1704 in our case, and the third one is sum of squares of the residuals, which is more and more similar. Sum of the squares within the treatment or sum of the squares between. So SSR is something which is a term which we use for sum of squares within the treatment. So what do I do for that sum of squares within the treatment? Logically speaking, I should get it as the subtraction between the two. So I should get it as 41,140. But what is the way I can compare it? The way I can compare it is, I should, for the first instance, I find out the variance with respect to its mean, or sum of squares with respect to its mean. Find out the sum of squares of Kohli with respect to its mean, and sum of squares of Rohit with respect to its mean. So what does that mean for us? I take each observation of Dhawan and subtract the Dhawan's mean from it, which is this one, and do a square. This is what is the sum of squares I am talking about. So for all the 14 matches which he has played, I'll do the similar kind of an analysis. So these are the sum of the squares with respect to Dhawan from the corresponding mean of Dhawan itself. The same logic I should use for Kohli. Each observation minus the mean of Kohli. Earlier, when we did the total sum of squares, we took it with respect to the overall data. But here, the overall mean. Here we have taken with respect to the mean specific to that particular treatment. So if I do this, these are the sum of squares with respect to Kohli. And finally, if I am doing the same with respect to Rohit, each individual item minus the mean of Rohit square. So these are the sum of squares with respect to Rohit. Now, when I add up all these things, it should come out as the difference of the SST and SSB. Then only all the calculations we have done are more or less appropriate. If you see, it's exactly coming up, which means whatever the exercise we have done till now, in terms of partitioning the variability, we are quite successful with respect to that. Right, so this is the total sum of squares. This is the sum of squares between the observation, between the treatments, and this is the sum of the squares residual or probably within the treatment, within each of the treatments. The sum of the squares is typically given by 41,140. So let's go back to our data. So from this, what we are looking at is we are able to compute the mean. This we are done. We have also found out the treatment effect of each one of them. The particular treatment mean minus the overall mean. We are able to do that. Yeah. Now, when I want to find out the overall variance, not the mean, the overall variance in this kind of a scenario, we are finding it out using the sum of squares of the residuals divided by n minus k. Okay, now that we got our sum of squares of the residuals, we can very well find out the overall variance. What is the overall variance? Sum of squares of the residuals divided by n minus k. K is the number of treatments as we started off the exercise. The number of treatments is 3 and n is 41. So this comes out to dividing by 38. The overall variance comes out to 1082 in this case. So the overall variance also is something which we were able to find out. It comes out to 1082 in this case. So just to summarize what we have done, the total variance from our data can be computed as the variance within each treatment, which was sizably high in our case. The variance within each of the treatments is working out to around 41,140, whereas the variance between the treatment means, which is coming out to around 1,740. The way we compute our the sum of squares between the observations, between the treatments, is nothing but that specific treatment mean minus the overall mean whole squared, sum of squares of the differences between the overall mean and the specific treatment mean multiplied by the size of each of the treatments. So the overall variance is going to be this particular number, and we also come out with, okay, the total sum of squares we are able to find out. Each one of these things we were able to compute. Now, the variance between the treatment means, if at all I have to test out whether the variances between variances result in significance or not. If I have to test whether the between the variance result that I have got 1700, is it significant or not? For that, we are employing what is called as a F-test. You see here, it is identified that to test out for the significance, we are employing a test statistic, the between sum of squares by k minus 1. Okay, let me find out these two things. Between sum of squares by k minus 1 divided by The residual sum of squares by n minus k. Residual sum of squares by n minus k we have already found out, which is nothing but the overall variance between sum of squares by k minus 1. K is 2, 3 here. So between sum of squares by k minus 1, which is 2, comes out to 852. The between sum of squares by k minus 1 divided by residual sum of squares by n minus k is what we are going to test out. So the f statistic which we have to compute is nothing but this number divided by overall variance. So this has come out to 0.78, and the degrees of freedom is k minus 1 comma n minus k. So based on this, I should be able to put up the critical value. Critical value, if I am trying to find out with respect to k minus 1 and n minus k degrees of freedom. So let's say I am looking at 2.5%. The k minus 1 is 2 and n minus k degrees of freedom is 38. So corresponding to this, the critical value is 4.07. And so as long as our value lies outside the 4.07, we will go ahead. If the F statistic which we have computed is outside 4.07, then we can very well say, we can very well reject the null hypothesis and we could have gone with the alternate hypothesis. Whereas in this case, I cannot reject that kind of a scenario. So at least at 95% level of confidence or 5% level of significance, we can easily conclude that there is no big difference across the means of the three sets of treatments. Because if there had been a significant difference, then obviously your F statistic calculated value would definitely be higher compared to the critical value of 4.07, and it would have got concluded that there is a significant difference across each of the observations. So the moment we see that there is no significant difference, probably we don't need to proceed further. But yeah, if we have to check out some other example, seeing that there should be a significant difference, let me just write out another example so that we can quickly work out. If I'm taking some other data set to quickly work out on the same, 36, 28. So just quickly repeating the entire process. So in this case, for me, the k number of treatments is 3. See, we just need to find out whether the means are uniform across the 3 treatments that we have identified. So again, going ahead, k is 3. Then we have n, which is the total number of observations across, which is 27. Quickly doing it because it's the same thing. N1 is 10, N2 is 8, N3 is 9. Then we are talking about y1 dot and y1 dot bar. So y1 dot is the summation of all these 320, and y1 dot bar is nothing but this divided by 10, so which is 32. Same logic, y2 dot is the summation of all these, and y2 dot bar is this number divided by 8. Similarly, y3 dot is the summation of all these, and y3 dot bar is nothing but this value divided by 9. Similarly, y dot dot is the summation of all these, and y dot dot is the summation of all these, and the y dot dot bar is nothing but this divided by 27. So this is basically the overall mean, and these are primarily the treatment means. So based on that, I can get the treatment effect for the first one. Treatment effect for the first one is the first mean compared to the overall mean. The treatment effect of the second one is the second mean minus the overall mean. And treatment effect of the third one is the third mean minus the overall mean. So basically these are the three differences that are existing. And what we have also done earlier is we find out the total sum of squares, SST, the sum of squares between, and sum of squares which are residual or within. How do I find out the total sum of squares in this? Each of the observations, I subtract the overall mean, which is nothing but y dot dot bar. I subtract the overall mean and do the square. Sum of squares of all values from the overall mean. So I'll find out the sum of squares of the values from the overall mean. These are the values from the overall mean. So the sum of squares total is coming out to the summation of all these values, which is working out to 1470.52. And the same logic, if I am doing it for the sum of squares between, which is nothing but the n1 times the first one mean, or probably the treatment effect, which is nothing but the first mean minus the overall mean. So the treatment effect square, probably I can do directly that. The treatment effect square plus the size of the second treatment multiplied by the treatment effect square plus the size of the third treatment multiplied by the treatment effect square. So overall it is coming out to around 356.09, which means my residual sum of squares or sum of squares within should definitely come out as the difference between the two, which is 1114. The other way that we can find out the residual differences, sum of squares of the residuals, is like the way we have done earlier. Each value subtract that corresponding mean and do a squaring. From each value subtract that corresponding mean and do a squaring, which works out to these numbers. Similarly, you do the same in case of second. Each observation you subtract the corresponding mean y2 dot and do a square. So these are the numbers. Similarly, for the third one also, each value minus y3 dot, do a squaring. Alright. So the summation of all these things should definitely be equal to 1114. So just if I have to do the summation of all these three, obviously it comes out to 1. So at least this is just a simple way to verify the entire process. So as per the null hypothesis, what is the null hypothesis? The means are equal. So the other way of writing the same is probably TE1, which is the treatment effect of each one of them, treatment effect of 1 equal to treatment effect of 2 equal to treatment effect of 3, all of them should be equal to 0. If they are not different, if they are not equal to 0, so we have to really prove, we have to really use our mechanism to test out. For that, what is that we are saying? For that, we are finding out what is called as overall variance, and that overall variance, we are simply calling it as SSR divided by n minus k. N minus k is 27 minus 3, 24. So overall variance works out to 46.43, and so overall variance is 46.43, and we are also looking at SSB by k minus 1, because using these two only we are actually finding out the F statistic. So SSB by k minus 1, 356 by 2, so this is coming out to 178, and based on this I am finding out the F statistic. The F statistic is nothing but SSB by k minus 1 divided by the overall variance, coming out to 3.83. So based on this, I should be able to find out the critical value from the F tables. So at 5% level of significance, we are talking about 2 degrees of freedom and 24 degrees of freedom, working out to this number as 3.4. If it is 3.4, our calculated F value is above the 3.4 limit, which means it is in the critical region or in the rejection region. So I can very well say at 5% level of significance that there is a significant difference in the means of the data. There is a significant difference in the means of the data. That is what can very well be found out. And now the next aspect comes in terms of finding out. So just going back, the significance test is SSB by k minus 1 divided by SSR by n minus k, and we are doing the appropriate testing, and the adequacy of the model can also be tested by plotting the residuals and then checking out the normality of the data, because whatever the two key assumptions we have made, only under those assumptions being satisfied, the entire thing can be adhered to. Otherwise it's going to create an issue for us. So that's one of the prime reasons we should be very careful in terms of using the result whatever we have got in the process. Only under the assumption that the population is normal and the variances are more or less the same, we can use this ANOVA model. And now that in this example we are able to find out that there is a difference, so how do we proceed further? The proceeding further is what? If I have to define the interval for each of the means. Now that we have got that the means of each of them is something like this, or probably the means of each of them is something like this, then I am more interested in defining the 95% confidence interval for each of them, so that I want to see which of them are significantly different and which of them are not. So in this case, if I have to find out the confidence interval for a single treatment mean, so we'll look at two aspects, right? Probably we'll call it confidence interval for single treatment mean. This is one aspect we'll see. So we can very well find out whatever is the mean that we have got, we can do an adjustment with plus or minus t times the standard error, sigma by root n. So what is the t? T is the value based on. So probably I can say the for let's say for 1, for the first item I want to find out the confidence interval. I'll find out as the treatment mean 1 or probably y1 dot bar plus or minus t times sigma by root n. Sigma by root n. And here the probably I'll call it as n1. So the sigma is the overall standard deviation. Sigma is the overall standard deviation which we have computed. This is the overall variance. So probably taking the square root of this will give me the overall standard deviation. So in this example, the overall standard deviation is working out to 6.8. So what do I find out here? I will for y1 bar, it is nothing but y1. I'll take both the so we need to find out the n minus k degrees of freedom, the t value corresponding to n minus k degrees of freedom. So t critical value. What is the t critical value for us? We can look out into the tables. For a 5% probability and 24 degrees of freedom, the t value is coming out to 2.06. So corresponding to this, what is the value that come out? The minimum interval is 32 minus 2.06 times the standard deviation, which is 6.81 divided by square root of 10. So the minimum value comes out to 27.55, whereas on the other side I can also take 32 plus 2.06 times the standard deviation by square root of 10. So for the first one, the range is between 27.55 to 36.44. That is the kind of a range that is occurring for one single observation. For one single observation, that is what is the value that is coming out to. For the first treatment mean, the 95% confidence interval is this one. Whereas for the second, the same logic, if I am using this minus 2.06 times the standard deviation by square root of 8. So 23.15 to this plus 2.06 times the standard deviation by root 8. So overall it is saying that the limits for the second one, 95% confidence limits are 23.15 to 33.09. Whereas for the third one, if I see 37.22 minus 2.06 times the standard deviation by square root of 9. This is what is an important result for us, because it is it is lying between 32.53 to the same logic if I am applying here, 37.22 plus 2.06 times the standard deviation by square root of 9, which works out to 32.53 to 41.91. This is These are the individual confidence intervals for the individual treatment means, and that is what is one set of analysis which we typically do. And the second set of analysis which we are getting in the same process is setting out the confidence intervals for a pair of treatments. So between 1 and 2, between 2 and 3, what is the difference? This is what, if I have to try out, I have to find out the confidence interval between the pair of treatments. What we can very well do is we can find out the mean of, we can take the mean of each one of them plus or minus t times, again the standard error, multiplied by square root of 1 by n1 plus 1 by n2, sigma into square. So if I apply this kind of a formula, I should be able to find out again the 95% confidence interval corresponding to the pair of the differences differences between a pair of treatments rather than an individual treatment. We are trying to find out the difference between the pair of treatments using this approach. The same logic if I am taking it, so probably y1 dot and y2 dot if I want to find out. So what do I find? First I'll find out the difference between y1 dot bar and y2 dot bar. We'll find out the difference between y1 dot bar and y2 dot bar. So minus, again the t is the same, times sigma is also the same, times the square root of 1 by n1 plus 1 by n2, 1 by 10 plus 1 by 8. If I am doing this exercise, it is coming out to minus 2.79. The lower limit between the differences is coming out to minus 2.79, whereas the upper limit is coming out to this minus this plus 2.06 times sigma times square root of 1 by 10 plus 1 by 8. So this is coming out to the 95% confidence interval between the differences of y1 bar and y2 bar is somewhere between minus 2.79 to plus 10.54. And because that difference is containing 0 also, the interval is containing 0, we cannot say that there is a significant difference between the 1 and 2. So we cannot conclude any kind of a significant difference between 1 and 2. The same. So, but overall we have seen that they are all not equal, which means at least one pair you should find that there is an issue. So let's say I am trying to find out y2 dot and y3 dot. The same logic if I apply, the y2 bar minus y3 bar minus 2.06 times the standard deviation times 1 by 9 plus 1 by 8. So the error is around minus 12.4. The minimum difference as per 95% confidence level is around minus 12.41, and on the higher side this minus this plus 2.06 times the standard deviation times 1 by 9 plus 1 by 8. If I do this, this is working out to minus 5.71. So the 95% confidence interval of the differences between y2 dot and y3 dot is minus 12 to minus 5, and 0 is not present in this interval, which means definitely y2 is significantly lesser than y3. y2 is significantly lesser than y3. The same logic if I do y1 dot and y3 dot. All the pairs I can do this kind of an analysis wherein I am looking at, okay, y1 dot minus y3 dot minus 2.06 times the standard error times 1 by 10 plus 1 by 9. So the minimum side is minus 8.19, whereas what is the maximum side? 32 minus 37.22 plus 2.06 times 6.81 times 1 by 10 plus 1 by 9. So this is minus 2.25. So this is also saying that there is a significant difference between y1 and y3 also. So the way probably I can write it is, if I am looking at the means, y1 bar is definitely less than, sorry, first the minimum most is y2 bar. y2 bar is less than, y1 bar is less than y3 dot bar. But in this, because y2 and y1 do not have much of a difference, we can club both of them and we can underline these two things. We can underline y2 and y1, saying that there is no significant difference between y2 and y1, whereas these both are significantly lesser than y3. Right, let me just check out the difference plus 2.06 times this value times, yeah, so that is a kind of a significant difference that is existing. Right, so y2 and y3, y1 and y3, in both the cases there is a significant difference that is existing between the two, which is a clear indication that y2 bar is less than y1 bar less than y3 dot bar. But y2 dot bar and y3 dot bar we will be joining, y2 dot bar and y1 dot bar we would be joining, as the difference between those two pairs is not significant. So that is the kind of analysis. So probably in this I will underline these two things. Right, I should be underlining those two. So look at it like this. I have underlined y2 dot and y3 dot bar, but did not include the y3 dot bar. y1 dot bar and y2 dot bar are underlined, but not y3 dot bar, because y3 dot bar is definitely more than the other two. So the least significant difference between the two can very well be understood using this kind of a formula. P times the overall standard deviation times square root of 1 by n1 plus 1 by n2. Let me just see if I have applied the same logic across. Oh, here we did not actually apply the square root. Okay, still that's not a big deal, right? Square root of 1 by n1 plus 1 by n2. So minus 15 to minus 2, whereas in this case it is minus 2 to 10. So here also let me see if things get improved. So it comes out to minus 11 to 1.2. Yeah, so there is no significant difference between y1 and y3 also. So overall, probably y1 and y3 don't have a difference. So I would be highlighting these two with a red, but y2 I will not highlight because y2 is pretty much lesser than, significantly pretty much lesser than the other two. Y1 and y3. So y2 is less than y1 and y3. So there is not much of a significant difference between y1 and y2. So y1 and y2 also will have to put one red. Y1 and y2 there is not much of a difference. Y1 and y3 there is not much of a difference. But so there are two underlinings we do. One is between y2 dot and y1 dot, one underlining. The other underlining is between y1 dot and y3 dot. So these are the two sets of underlinings we do in the entire data, but there is no underline between y2 dot and y3 dot because there is a significant difference between the two sets of values. So because there is at least one difference between the different sets of values, the ANOVA result says that all of them are not uniform across. So that is what is the typical analysis across the groups, and we will find that there is a significant difference that is existing across some of the groups, whereas across some of the groups the difference does not exist. All right. So you have to be very comfortable in doing these kind of numericals and involving the calculations of ANOVA as well as the interpretations of ANOVA to a comfortable extent. Thanks a lot for listening to this session. If you have any further queries, you can give me a call on the number which I have highlighted below, or you can even send in an email at the email address which I have given there. Thank you very much.